Hello my dear, welcome to IMS GATE Academy. I hope you are all good and your preparation going to be in a right direction. I am Pragyabrat, faculty Department of Mechanical Engineering. So beta, we will start for the today's class. We will start the observation. What is that? A different observation that throughout the thermodynamics, we have to discuss about all the possibilities for that, and in that sense, we have to discuss about some good observation. That means you have to do for that very accurate revision for that. So first observation is that beta. The first observation is that. Please give me a reply for that one. Please give me a reply for that one, beta. That is first observation. Observation number first. First is what? First observation is what, beta? First observation, okay? First observation. This is the first observation, and the first observation is, okay? The first observation is all the isothermal process, all the isothermal process, all the isothermal process, that means every isothermal process, that means what you think that all the isothermal process must be reversible process, Please check, this is true or false. This is true or false. Please check, beta. This is true or false. Please give me a reply. All the isothermal process, that means you think that all the isothermal process must be reversible process. Please give me a reply. True or false? This is true or false? Please give me a reply. This is true or false? Please give me a reply. This is true or false? Please. This is true or false? Everyone, please reply in the chat box. This is true or false? That means all the isothermal process occurring in this for the system must be reversible. That means you think that there is an isothermal process and that isothermal process is reversible. It must be or not? Please check. So beta, what is the reversible process? If you think that reversible process, if the process is right, the process is reversible, that means that process is both internally reversible as well as externally reversible. Yes or not? Externally reversible. Okay, we'll check. Start with that. That means if you think that the reversible process, that means it will be externally as well as internally reversible. Okay. Now, let's take one example. That means if there is a piston cylinder arrangement, this is your cylinder and that is your piston. Okay. There is a piston cylinder arrangement. Let's suppose this is your piston cylinder arrangement and this is your system boundary. This is your system boundary. Let's suppose this is your system boundary. Okay. This is your system boundary. Let's suppose this is our system boundary. Okay. Let's suppose any system and that is your system boundary, and that system boundary have a temperature. Let's suppose T1. Let's suppose this system boundary temperature T1. T1 is the system boundary temperature across which heat will transfer. So we have to transfer the heat, across which heat will transfer through a thermal reservoir. Let's suppose T0 is the thermal reservoir. And if heat will transfer from the surrounding to the system, automatically that means T1 is much less than T0. That one, okay? Now, see my dear, this is very important that if you transfer the heat and if you want that the system is isothermal, how do we do? So there is a boundary temperature and there is a finite temperature difference. This is your finite temperature. So what you do, you transfer the heat and you want that the system temperature T1 is constant throughout. You want that the system temperature constant. Why? Because this is isothermal process. So you have to make this system as an isothermal system process. How to make? If you transfer the heat and you have to push the piston, against the atmosphere, against the surrounding, so that there will, so if you transfer the heat Q, that means if you transfer Q is equal to delta U plus W. And now when the system is isothermal, so delta U is 0. That means what amount you heat will add to the system 1 to 2 is same amount of the work will deliver 1 to 2. Accordingly, the process is isothermal. Now, whether this process is reversible or not? See beta, yes, this process is internally reversible. Yes, this process is internally reversible. Why? Because you supply the heat, the system internal energy will increase. So you want that the system temperature will remain same. So you push the piston upward so that its temperature remains constant. But while you transferring the heat, the transfer of heat through a finite temperature difference. That means their delta T is equal to T1 minus T0. So this is not equilibrium temperature. That means this is not 0. It is not 0. That means it is not tends to 0. Yeah, you can say that it is not tends to 0. It is not tends to 0. That means the system is externally irreversible. That means system is externally irreversible. Externally irreversible. So if the system is externally irreversible, so in this process the system is externally irreversible. So it is irreversible. So if the externally irreversible, internally reversible, so totally it is irreversible. Totally it is irreversible. So this statement is false. This statement is false. See my dear, see, if it is written like that, all the isothermal process may be, then it is okay. Then it is okay. May be reversible, but it is not must be reversible. See beta, during the condensation and evaporation, during that the phase will change. During the condensation and evaporation, the phase will change. During the phase changing fluid, phase changing substance, there must be a temperature constant. Yes or not? During the phase change, the temperature is constant. Why? Because during that there is a latent heat will transfer. So during that the temperature is constant. Now the temperature is constant, that means it is isothermal, but heat transfer takes place through a finite temperature difference. That means it is external irreversible. That means it is internally reversible but external irreversible. So the total process may be irreversible. So it is not necessary that all the isothermal process must be a reversible. No, it is not. Yes, all the isothermal process may be internally reversible and may be externally irreversible. In that sense, this statement is true. Okay, so so that if you make the process is externally reversible, you have to supply the heat through infinite small temperature difference. That means if this is T0 and if the system boundary temperature is T0 minus delta T, so that there is a Carnot. What is the Carnot? Carnot, it is a heat transfer through infinite small temperature difference, and accordingly we push the piston upward. So the Carnot, if it is work on the Carnot cycle during the heat transfer at isothermal, so isothermal heat transfer is a reversible when there is a external as well as internal reversible. So this is internal reversible but external irreversible. So it is the isothermal process, but that isothermal process may be irreversible process. So the isothermal process may be reversible process and may be irreversible process. Isothermal process, when there is a reversible process, when internally, that means the piston movement is very slow and also the heat transfer through infinitely a small temperature difference. That means in this sense, delta T tends to 0. In this sense, it is a reversible process. But if the internally reversible, that means you move the piston very slowly, but the heat transfer is more temperature difference. So in that sense, this is external irreversible. External irreversible. So this is statement is false. Now we have to take next statement. What is the next statement? The next statement is what is the next statement? Next statement is cyclic integration dq. If you take a cyclic integration dq, may tends to 0 for irreversible process. This is true or false? Please reply in the chat box. This is true or false? This is true or false? That means cyclic integration of dq may tends to 0 for irreversible process. This is true or false? Let's check. So let's check. So what is the origin? How to check that one? That is the more important. What is that? If you design a heat engine, this is your heat engine, okay, it's take a heat QH from a high thermal reservoir TH and reject a remaining heat dump to the sink at TL. Okay. During that, if we take, this is our system, heat engine is our system, it will produce a work W. It will produce a work W net. Now my dear, if you make this system is irreversible, why? Because this is an irreversible process. So if it is irreversible, what is the cyclic integration? What is the cyclic integration for this one? You know that the cyclic integration is summation of all the heat transfer for the system. So QH will into the system positive minus QL is negative. So this is your, and this is your first law of thermodynamics dW, and that is your W net. Yes or not? Yes or not? dQ is equal to W net. dQ cyclic integration of dQ is equal to cyclic integration of dW, and cyclic integration of dW is W net, and cyclic integration of dQ is the QH minus QL. Now see this one. So what is this? This is there. This maybe tends to 0. How? See beta, if the cycle is so irreversible internally, that means this is a irreversible. That means you make a cycle such a way that is highly irreversible. So all the heat we will take to the system will be lost to the surrounding. So this loss is due to the irreversibility present in the heat engine. So this is the irreversibility. This is not due to the irreversibility. QL will reject from the heat engine. This QL is rejecting either the system is 100% reversible, so that this is also will QL. So my dear, if there is a heat engine, see this one. If there is a heat engine and if you make a reversible heat engine, so there must be a QL also. Yes or not? Second law of thermodynamics. Clausius statement. W. Now, if we make this engine irreversible, heat engine irreversible, so in this sense also there is a work net, and also there is a heat will transfer QL irreversible to the TL temperature, and this is your QH to the higher temperature TH. So mind it beta, this QL must be there. Either the system is reversible or irreversible, so that it sometime is called unavailable energy. This is called unavailable energy. But if the system is so irreversibly unavailable energy is what? That energy we cannot utilize for the work potential. But if the system is highly irreversible, so there must be a heat loss. And this heat loss is due to irreversibility. So if heat loss is maximum, so W net tends to 0. If heat loss is maximum, and this heat loss is due to irreversible process. So beta, this heat will rejecting from the reversible heat engine. That means this is your unavailable energy, and this unavailable energy is not a energy which is work potential, but this heat loss is due to irreversibility. This is your irreversibility, and this irreversibility is lost opportunity to do work. So this is the irreversibility, and irreversibility caused that loss. And if there is a highly irreversible heat engine, so that heat loss is maximum. So if heat loss is maximum due to highly irreversible heat engine, so accordingly Q net tends to 0. Yes or not? Q net tends to 0. So if Q net tends to 0, so automatically cyclic integration tends to 0. That means cyclic integration may tends to 0 for irreversible process. This is true. So beta, it is not important to identify the true and false. It is important to how to analysis of this situation. So analysis is very important. So this is for the cyclic integration maybe tends to 0 for irreversible process is true. How? That is the reason. Okay. So this heat loss is due to irreversibility present in the system. Okay. Now this is second. Now third one is that. What is the third one? Observation third. You have to observe third number. A process with no net change in entropy. A process with no net entropy, no net change in the system entropy, no net change in the system entropy must necessarily be reversible and adiabatic. And this is true or false, please. This is true or false, please, everyone. This is true or false. That means a process with no net change in entropy of the system. That means entropy of the system. That means a process with no net change in the system entropy must necessarily be reversible adiabatic. This statement is true or false. Please check. This statement is true or false. These all the questions are coming to the MSQ type question. That means observation first, this is third, this is second, and this is first. So there is an option. First option is this one. Second option is this one. Third option is this one. And they are asking which of the following is correct option. So these may be construct in the MSQ type question. So accordingly, for that motive, we have to take this type of situation. Okay. So first we'll check the entropy change of the system. So delta S of the system. So first balance the entropy. So if entropy, this is our system, mind it beta, this is our system, let's suppose. This is our system, any system, and let's suppose there is a mass in, mass exit, heat in, okay, mass in, mass exit. So mass in, there is a entropy in, mass exit, there is a entropy exit, and there is a change in entropy of the system. Also there is a S generation is greater than or equal to 0. So what is the entropy balance? S in minus S exit plus S generation is equal to delta S of system, and that delta S of the system is S2 minus S1. Now this entropy transfer is due to heat and mass only, okay. So what is the heat in Q? Let's suppose the process 1 to 2, there is a heat transfer Q1 to 2. So heat in, that means Q1 to 2 divided by temperature. What is the system boundary temperature? Let's suppose the system boundary temperature is T. So T in, there is a no exit. So if we take, there is a in and also there is a mass in. So MISI exit, MESE, there is a exit condition, is equal to S2 minus S1. Now my dear, and there is a generation, na? This is generation, S plus S generation is equal to S2 minus S1. No problem at all. Now see my dear, if we take the process with a no net entropy change of the system, that means if we take, this is 0, this says that entropy change of the system is 0 according to the question. It is say that it is 0. Now if this, let this, for the simplicity, take this is change is 0, that means closed system, this is 0, okay, this is 0 we take. So what is the entropy change of the system? That means 0, is equal to Q1 to 2 divided by T plus S generation. Now my dear, this is heat transfer due to entropy transfer by heat, and this is entropy generation due to irreversibility. Okay. Now when this is 0 and this is your delta S of the system. So delta S of the system when it is 0, there are two conditions. First, let's suppose this equation is in plus X, okay. Let's suppose the heat will transfer from the system to the surrounding is, let's suppose if this is your system and heat will out from the system, let's suppose Q through at this boundary temperature T. So this is negative, so minus let's suppose X, and let's suppose the entropy generation is always positive, that means this is always greater than or equal to 0. So this is, let's suppose X. So in this case this is 0. So this X is non-adiabatic, that means heat transfer is there, and there is a irreversible. So irreversible non-adiabatic process may be isentropic. Yes or not? This is system entropy, that means this is isentropy. So isentropy will come when there is a non-adiabatic and irreversibility. So non-adiabatic, that means it is minus X and it is plus X, so it may be 0, that means isentropic process may be non-adiabatic, irreversible. But if there is this is 0 adiabatic and this is 0 for reversible. Reversible adiabatic process must be isentropic process, but the isentropic process may not be reversible adiabatic. It may be irreversible non-adiabatic. So what is your statement? That means all the process with no net change in entropy of the system, that means entropy of the system is 0, must be necessarily reversible adiabatic. No, this is false. Here maybe, here maybe, it may not be, matlab it is not necessarily. That means yes, it is written as that a process with reversible adiabatic process, a process that is reversible and adiabatic must be isentropic. That is true. Reversible adiabatic process must be isentropic. That means entropy change of the system is 0. That is true. But a isentropic process may not be reversible adiabatic. May not be reversible adiabatic. Simply beta, simply what is that? Delta S of the system. What is the delta S of the system? Only heat transfer. We are talking about only heat transfer. Q1 to 2 divided by T plus S generation. Yes. This S generation is 0 when the process is reversible. That means internal reversible. And this is greater than 0 when the process is irreversible. Yes or not? Irreversible. And this heat transfer will be positive if add heat. This will negative if reject heat. And it will 0 when adiabatic. Yes or not? That means if this is your, take one, this is 1, 2 and 3 and this is 1 and 2. Take, what is the possibility is 0? What is the 0? If first, if the process is reversible, from that one, process is reversible plus adiabatic. That sense delta S is equal to 0, that means isentropic. Yes or no? Isentropic. But the possibility is other two, that means reversible, the process is reversible but non-adiabatic. Reversible but non-adiabatic, the system entropy is not changing. Let's suppose the second case, the process is irreversible plus non-adiabatic. Non-adiabatic, reversible and non-adiabatic. In this sense, also delta S 0. That means isentropic. That means irreversible, that means let's suppose this is a plus x, non-adiabatic, let's suppose it is minus x. So if you add this two quantity, this must be 0. That means isentropic. That means reversible adiabatic process must be isentropic. Reversible adiabatic process must be isentropic. But isentropic process need not be irreversible adiabatic process. Why? Because it may be irreversible non-adiabatic process. Clear? Take any position. If we this will positive, heat added and reversible non-adiabatic. Negative 0 non-adiabatic. 0 adiabatic, irreversible, not isentropic. So isentropic condition always when there is a, that means a reversible adiabatic process must be isentropic, but the isentropic process need not be reversible adiabatic. Why? Because this is irreversible non-adiabatic process. That is very important, I am telling you. That is very important, okay? So this is the second observation. Now the third observation is that third observation is that see this one. Third observation is that what is the third observation? Let's see beta. Third observation. This will delete, no problem. One second. Now, let this one, this is also same, a process with zero net change in entropy, zero net change in entropy, zero net change in entropy necessarily must necessarily be isentropic. No. It is true or false? It is very easy. True or false? It is false. Yes or not? It is false. Yes, it is false. Why? Because a process that zero net change in entropy must be necessarily isentropic. No. Let's suppose delta S is equal to what beta? S2 minus S1. And this S2 minus S1, a process with is equal to 0. Let's suppose this is 0. That means S1 is equal to S2. You cannot say that it is isentropic. We cannot say it is isentropic. No, we cannot say. How? See, if this is TS diagram, T and S diagram, okay, and let's suppose delta S is 0, that means initial and final point are same. Let's suppose this is your process and there is a point 1 and 2 is there. So at this point S1 is equal to S2. At this point S1 is equal to S2. Yes or not? S1 equal to S2. But let's suppose this is process. But what is this one? Here, let's suppose this is S1. Let's suppose here this is S2. So here S1 and S2 are same. So a process which have a change in entropy is 0. We cannot say that all the points have a same entropy. No, it may be vary. That means it is like a property. That means entropy is what? A property. That a property change is equal to 0. It is not necessary that entire process that is a same value. No. Yes, it is initially and finally same. It is not necessary throughout the initial and final entropy are same. Okay, like that you can say that. That means this is not isentropic. That means a process that have zero net change in entropy, you cannot say that this is isentropic. Why? Because see, if you think that delta S is equal to Q1 to 2 process by T plus S generation. Yes or not? If this is a 0, that means isentropic. This is isentropic, but it is not necessary that a process with zero net change in entropy. So zero net entropy change may not be isentropic. Why? Because may not be isentropic. Why? Because if there is a isentropic, this is your plus X minus x, and this is plus x. So in that sense it is 0. So isentropic process may be irreversible adiabatic process, may be reversible. That means a reversible adiabatic process must be isentropic, but that means if there is a net change in entropy must be 0. It is not necessary that isentropic, that means throughout the process 1 to 2 the entropy is same. Throughout the process 1 to 2 is entropy same, but if there is a process in which 1 and 2 point are same, so you cannot say that at this point entropy S1 equal to S2. No. At this point S1 equal to S2. No. At this point S1 equal to no. So at this point S1 equal to S2, it is not necessary that entire process has the same entropy. No. So it is false. It is false. Correct? Now, take the second observation. What is that? Entropy of a fixed mass, the entropy of a fixed mass is fixed, that means closed system, of an ideal gas, decreases in every isothermal compression. Let's check this is true or false. Let's check this is true or false. Please, everyone, this is true or false. That means the net change, the entropy of a fixed mass of an ideal gas decreases in every isothermal compression. There is a isothermal compression. Let's check. This is very important question. The entropy of a fixed mass of an ideal gas, that means there is a container. In this container there is ideal gas. So for the ideal gas, if there is a compression isothermally, so the entropy will decrease or increase or remain same. They are asking entropy will decrease or what if there is a isothermal compression. Let's check. So if you check that, so what is, how to check? This is very important. We know that TdS is equal to dH minus VdP. You can use this TdS second equation. Now, what is dH? dH for ideal gas is what? Cp delta T, so Cpt. dH equal to Cp delta T. Why? Because ideal gas. Now, and there is isothermal, so this is 0. That means isothermal. That means dH is equal to 0. That means dH is equal to 0. Now, if so, what is the equation? TdS is equal to minus VdP. Yes or not? Now, if you take a entropy change, that means ds. What is the ds? Minus VdP divided by T. Now, beta, see this one. The volume, this volume is always positive. This is volume is always positive quantity. It may be 0, but it is a positive quantity. That means this is volume is a positive quantity. This is always positive, either compression or expansion. Volume will decrease. In the compression, volume will decrease, but that decrement is always positive. It is not like that negative. Delta P is positive. Change in pressure is positive. Why? Because during the compression, pressure will rise. So during the compression, if you compress it, so its delta P will increase, pressure will increase. So this delta P is also positive. Now, this temperature it is in also positive. Why? Why? Because this is absolute temperature. Absolute. Always take in TDS, there is an absolute temperature scale. So all this, that means ds is equal to negative. ds is negative. ds is negative. That means the entropy of a fixed mass of an ideal gas decreases in every isothermal process. This is true. Very important, I'm telling you. This is true. So these all are options will be developed a question which is MSQ type question, and this is really very important and very confusing, I'm telling you. That means how to deliver the expression, how to think that expression, how to solve that statement with your logically mind. So it will creates your mind in the logic. So the entropy of a fixed mass of an ideal gas decreases in every isothermal compression. Every isothermal. That means a closed system, if you compress it isothermally, its entropy always decrease. That means S2, this is delta S, that means this is delta S, that means S2 minus S1 is less than 0. That means final entropy will less than the initial entropy. Okay. Now, take the next one. Take the next one, beta. Take the next one. Take this one. Observation number 3rd. A spring is stressed by spring is extended by a tensile force. That means you apply the tensile force. What? F is equal to 1 kilonewton. Okay. Force isothermally stressed at temperature 300 Kelvin, room temperature approximately. What is the rate of change of entropy? What is the rate of change of entropy for the spring? For the spring per unit length. Per unit length. Just try to solve. That means a spring. There is a spring is there. So this is your spring. Let's suppose this is your spring. Okay, this is your spring. And we take this spring as our system. This spring is our system. Let's suppose this spring is our system. Now you have to apply a tensile force. If this is applied force, this is the system spring as a system. So on the system you have to apply the force. Okay, now how much? 1 kilonewton. 1 kilonewton. Okay, on the system you apply the force. Okay, isothermally, that means if you apply the force at a temperature fixed, it is your 300. That means its temperature doesn't change during the expansion or compression. It doesn't change. Now, what is the rate of entropy change for this spring per unit length? So we know that TdS is equal to du plus PdV, yeah, work. That means work. TdS equal to du plus, that means you know that now this Q is equal to delta U plus W. Okay, and the spring is extended slowly. This is slowly. Extended, a spring is extended slowly. Slowly by a tensile. So you have to express it slowly. So the work is applied irreversible work. So this is your reversible work. And what is the reversible work? So what is the reversible work? So if you reversible, yeah, if you apply this one W, and that W is a spring work, W of spring. Okay, and it is slowly, so this is your TdS. So this is delta U plus work due to the spring. Now you have to apply the force. So what is the spring work? Spring work. So if you apply the force on the spring, that means spring will try to compress it. Spring will try to compress it. What is the force? This is the minus F of the spring into the displacement. Let's suppose delta x. Okay, delta x. Now, this is what is the C delta T, and this delta T is 0. Why? Because isothermal. Isothermal. So what is that? TdS is equal to minus F of spring into delta x, right? So we have to find per unit. So ds, entropy change per unit length, is equal to minus F of spring divided by T. What is the spring force? 1 kilonewton, 1 cross 10 to the power 3 divided by this temperature is 300. So this is what beta? 10 by 3 negative. 10 by 3 negative. So it is your 3.33 minus 3.33 joule per kg per joule per meter. Joule per meter, या joule per unit length Kelvin. Take per meter या per mm. So this is negative. That means if you stretch the spring, the important thing is that anyone can ask you that if you stretch the spring, if you want to stretch the spring entropy will reduce. That means if you stretch the spring entropy will reduce. Why? Because the spring want to compress it. If you compress it, spring want to expand it. So during the expansion, entropy will. So during the compression, if it will compress, so expansion entropy will So this is a decrease. That means if you want spring want to compress stressed, so the spring entropy will reduce. Delta S of the spring will less than 0. This is very important. This is very important due to this derivation. So if you stretch the spring entropy always decrease. Spring entropy always decrease. If you stretch anything, that things have to reduce its entropy. Now, next one is, next observation. If you take this work, is equal to minus 1 to 2 VdP. What do you think? What do you think, beta? This is what? First, this 1 and 2, first you think that this is for the reversible work. Matlab that means for open system, flow work. This is for the flowing system. This is for the flow system. That means this is your control volume work. Okay? That means open system work. Okay? And the negative, that means work output. Work output. This is your work output. And this 1 and 2 are not a state point, it is inlet and exit cross section. It is a cross section, that means not a state point. Not a state point. It is a cross section, number first. And this equation is applicable for any reversible process. Any reversible process. That means reversible adiabatic, reversible isothermal. That means this is still that any, that means reversible adiabatic, reversible isothermal, like that. Okay? Any reversible process, and this is for the steady state, and for the steady state, this is for the steady state, no change in within the volume, steady flow with single inlet, single exit. That means the single stream, single stream, that means single inlet, single exit, and change in kinetic and potential energy are negligible. That means delta Ke and delta Pe are neglected. These are the complete information of this one. This is very important, I am telling you. That means this is, and this is your reversible. This is your reversible work, and particularly this is your internally reversible. Must be internal reversible. Must be internal reversible. So what is that? Reversible work. This is for the flow system, control volume, open system. Negative work output. That means like a turbine. Like turbine. like turbine. If there is a compressor, there is a negative, a positive sign is there. Okay, so this is negative. Now 1 and 2, this is an inlet and exit cross section, not a state point 1 and 2 within the system. Second, any reversible process, this is very important. Any reversible process, that means either for reversible adiabatic, reversible isothermal. Now next, steady state. Steady state, that means change in the property within the control volume. That means what is the property with respect to time within the control volume is equal to 0. This is for the steady, okay. And single stream, that means one inlet, one exit. Single stream, that means one inlet, one exit. And we can neglect the change in kinetic and potential energy. Okay. So I hope you all of you are enjoy this video lecture so that you can improve yourself, and you have to take the opportunity for that one. Now my dear, I give you one question also. Please, if you have this process to identify all the things process, this is your TS diagram, and that is for the ideal gas, and the process is like that. Different processes there. So this is A, B, C, D, E. You identify all the process. This is arrow, the direction of arrow it is. So you identify all the process A, B to A, that means process B to A, process A to C, process D to A, and process E to A. What is that? Identify. So example, if you take example, if you process B to A, what is the process B to A? Just apply equation TdS is equal to dH minus VdP. Okay. This entropy is constant, that means SA is equal to SB, that means this is 0. Okay. And this dH ideal gas Cp dt. Okay. So what is that? Cp dt is equal to VdP. Now my dear, here this is constant and a specific volume of the fixed fluid is constant. So if we, and from B to A, temperature decreases, that means delta T reduce. If delta T reduce, delta P also reduce. That means this is your, if delta P reduce, the P reduce, that means pressure will reduce, that means expansion. So process B to A is your isentropic expansion. Like that, you have just put your comment, all the process A to C, B, D to A, E to E. So this is your, this process you have to find it. This is isentropic expansion. What is this one? What is this one? What is this one? Just reply in the comment box so that we have to check in your chat box. Okay. Now, till now, that is the enough, and we have to meet in the future. We will meet for the some different topics so that you have to comfortable for that. Okay. Thank you. Bye bye.